Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics. We are going to see about feedback amplifiers, in which concept of the feedback, different types of feedback connections, and what is the effect of the feedback on gain, input impedance and output impedance. In the concept of the feedback, if you give the part of the output signal as feedback to the input signal, you can give it as a negative feedback or you can give it as a positive feedback. If it is a negative feedback, we already seen that it is an amplifier. If it is a positive feedback, it is an oscillator. If negative feedback is given, what are all the circuit improvements we are going to see now. So, this is the basic buildings or basic blocks to explain about the feedback concept. So, first the input signal is given to the mixer. This is the mixer circuit. The input signal is given to a mixer and the feedback signal is given to another input terminal of the mixer. If this is negative, then it is a negative feedback, and if it is positive, it is a positive feedback. So, the effective signals or the effective output is considered as Vi, and this input is given to the amplifier circuit and the output is produced, and some part of the amplifier output is taken as the feedback input, and this is the feedback network, and the amplification factor of the feedback network is represented as beta, and after the feedback network we are getting an output signal as the feedback signal, which is the signal given to the mixer. So, here amplifier is present and this is a feedback network, and A is the amplification factor of the amplifier and beta is the amplification factor of the feedback network. The effective signal, that is the input signal plus or minus the feedback signal, is now the error signal, or you can call it as the actual input signal to the amplifier, and this amplifier is amplifying the input signal here, and that is said to be the output. This is the concept of the feedback. And now we are next we are going to discuss about the connection at this output and connection at this input. That is, what is, you may take the voltage at the output as the feedback signal, or you can take the current at the output as the feedback signal, and you can connect this feedback output to parallel to the input signal or series to the input signal. So, according to the output signal which you are going to get, and according to the connection you are connecting to the input signal, the feedback concepts are varied. And we see that if the feedback signal is connected negative, it is a feedback amplifier or it is an amplifier. With this negative feedback, what are all the circuit improvements we are going to see is, if you give a negative feedback, then you will be getting higher input impedance, lower output admittance, lower output impedance, stabilized voltage gain, and improved frequency response, reduced noise and linear operation. So, these are the circuit improvements when you give a negative feedback to a circuit, and this is the various types of feedback. If you are giving, both voltage and current can be fed back to the input either in series or parallel. As I said in the basic diagram, you can take voltage at the output or current at the output, and you can give the feedback signal in parallel or series to the input signal. According to this concept, these amp feedback is varied. So, it is voltage series feedback, voltage shunt feedback, current series feedback and current shunt feedback. It means voltage series feedback. So, you are taking voltage at the output and you are giving the voltage signal in series to the input signal. Similarly, what is voltage shunt feedback refers to? So, you are taking again the voltage at the output of the amplifier and you are giving the feedback signal in parallel or in shunt to the input signal. In here, in current series feedback, you are taking the current as the output. Instead of the voltage previously, we are taking the current signal at the output and it is connected in series with the input signal. And for the current shunt feedback, it is the similar with the voltage shunt feedback. So, here voltage refers to connecting the output voltage as the input to the feedback network. Where you are connecting the output here, this voltage, the voltage is taken to the input of the feedback network. That is what here the voltage refers to connecting the output voltage as the input to the feedback network, and current refers tapping of the current to the input of the feedback network. Series refers to the connecting the feedback signal in series with the input signal, and in shunt it refers to the connecting with the parallel to the input signal we have discussed already. Series feedback connections tends to increase the impedance. Wherever you got series connection, it will increase the input impedance or output impedance wherever you got the series connection, and shunt connection, it will decrease the impedances. Voltage feedback tends to decrease the output impedance while current feedback tends to increase the output impedance. So, what does it mean? Voltage feedback tends to decrease the output impedance in the sense, if you take the voltage as the feedback signal, you have to take it parallelly. So, it means that you are having a shunt connection. So, if it has shunt connection, then the impedances will decreases. That is what here voltage feedback tends to decrease the output impedance, while current feedback tends to increase the output impedance. We know that current, you are tapping the current you have to take in series. We all know that if you measure the current in series ohm, it is common in all the ohms. For example, if R1 and R2 is connected in series, what is the current flowing through R1 is the same current flowing through R2. So, if you give a current output to as the input of the feedback signal, feedback network, you are taking in series. The current has to take in series ohm and it is given as the input to the feedback network. So, if it is series, then it will increase the impedance. Typically, higher input and lower output impedances are desired for most cascade amplifiers. For any amplifier circuit, we all know that it has to have high input impedance and low output impedance, because if that amplifier circuit is driven by a small signal source, if it has high input impedance only, the small signal source can be drive the amplifier circuit, and if it has low output impedance, then the output of that particular amplifier will be taken exactly, and the desired output will be obtained if it has low output impedance. So, for any amplifier circuit, for any electronic circuit, the circuit must have high input impedance and low output impedance. These two parameters can be given by the voltage series feedback network. About the voltage series feedback connection, we know that the voltage, the term voltage presents, then the output is the voltage signal, and if it is the voltage signal, the connection must be parallel, because if you take voltage across any parallel ohms, then the voltage is equal. Across any parallel ohms, the voltage is equal. So, if you want to take voltage, you have to take across the parallel connection. So, if voltage is given as the input to the feedback network, the connection must be a parallel connection here. So, for voltage it is parallel. So, if it is parallel, it means that you are taking the voltage output as the input to the feedback network. And here for series, the series part is for the connection in the input signal, part of the circuit. So, if it is series, then the feedback output has to connect with the series with the input signal. That is what it means. So, for voltage you are taking parallel, and the output is parallelly connected to the input of the feedback network, and here the output of the feedback network is connected in series with the input signal, and this effective signal is to the amplifier circuit, that is Vi. Here Vs is the input signal, Vi is the effective signal which is given to the amplifier, and Vout is the output of the amplifier, and some part of the output is taken as the input to the feedback network, and here the feedback signal is Vf. And what is Vf is beta, the gain of the feedback network or the amplification factor of the feedback network, into V naught. The gain is nothing but the output by input. Here the output is Vf and input is V naught for this particular feedback network, and for this amplifier A is the gain and which is given as the output by input. Output is V out, V naught, and the input is Vi for this particular network. And this is all about the voltage series feedback connection. And what may be the connection for voltage shunt feedback network? We have seen four different types of feedback connection: voltage series, voltage shunt, and current series, current shunt. So we have seen for voltage series feedback. Similarly, can you draw the circuit for voltage shunt feedback? So if it is voltage, always you have to take parallelly the output, right, if it is voltage, and this is for series. I am talking about the shunt. So you have to tell the connection for the shunt feedback. So shunt, in the sense, it is related with the input side. So input side, you have to connect the output of the feedback network in parallel with the input signal, that is for voltage shunt. Here I have given the circuit diagram for voltage shunt feedback. So here, if the output signal is voltage, always you have to take across the output terminals, and which is given as the input to the feedback network. And here if you see the connection at the input side, this is parallel connection because we got the term called shunt here. So if it is shunt, you have to connect it parallelly. So the input is here is Is, and the output of the feedback network is If. So the effective signal is considered as II. II is the signal, actual signal given to this amplifier, and here the output of the amplifier is V out, V naught, and this voltage is fed back to the as the input to the feedback network. So the gain of the feedback network is output by input. The feedback output is If divided by input is this output, the amplifier output, that is V naught. And here what is the gain of the amplifier? Output by input. Again, always if you talk about the gain of any circuit, it is the output by input. If it is a voltage gain, it is output voltage by input voltage. If it is current gain, it is output current by input current. So for the amplifier, output is V naught and input is II. So the gain is given as V naught by II. So this is all about the voltage shunt feedback. Let us have a break now. Welcome back after the break. We have seen two types of feedback connections. What are they? It is voltage series feedback and voltage shunt feedback. Now we are going to see about the current series feedback and later the current shunt feedback. For voltage series feedback, why this network is like this? Can you try to answer this? If it is a current, we all know that you have to take the output in series, because for current I already told you that you have to connect in series. So series connection is like this. Previously we have seen shunt connection here at the output for voltage. If you take the voltage from the output, why it has to be shunt is always when you calculate the voltage across the parallel arms, it is equal. So while you take the voltage, you have to go with parallel connection. While you take the current, you have to go with the series connection. So for current, you are taking the output in series, and it is given as the input to the feedback network, and this feedback network's output has to be connected again in series with the input signal, because it is again the current. It is current series feedback. So, you are talking with the term called current. So, you have to connect in series with the input signal, right. So, again this is the amplification factor of the amplifier. So, the output of the amplifier is I naught and the input is Vs. So, I naught by Vs is the gain of the amplifier, and beta is the gain of the feedback network. It is again the output by input. Beta's output is Vf, so it is Vf, input is I naught, so it is I naught, Vf by I naught. So, you can write the feedback voltage as beta I naught. And next final type of the feedback network is current shunt feedback. So, if it is current, you have to take the output in series, and if it is shunt feedback, you have to connect in parallel to the input side. Wherever you see the shunt feedback type, you will have the current source here. You have to note down in the voltage shunt feedback also. Here in voltage shunt feedback, if it is shunt feedback, you have to note this source is a current source. If it is series feedback, for voltage series also it is a voltage source, and current series, if you note down, it is a current source. So, it is a current series feedback, you are taking the current at the output. So, the connection is in series, and again this is the series feedback network. So, you are giving the output of the feedback in series with the input signal. So, these are all about the connection of various types of feedback networks, and also we have seen what is the gain with the feedback in this network, the overall gain AF. So, what is AF? It is the gain with the feedback. Gain with the feedback for the current series feedback network is the output I naught divided by Vs, input signal. This is the overall gain of the particular circuit, right. So, overall gain in the sense, what is the input you are giving and what is the output you are taking. So, here the output is I naught, the input is Vs. So, the output by input is the gain with the feedback. And now this is the comparison table for all the feedback connections, voltage series, voltage shunt, current series, current shunt. If you compare it with the feedback circuit, the gain without feedback, it is V naught by Vi for voltage series. With the feedback gain beta is Vf by V naught, and gain with the feedback is V naught by Vs. Similarly, for voltage shunt, it is V naught Ii. Why it is Ii? For shunt, we noted down that the source, signal source is current. So, for voltage shunt, it is V naught by Ii, and this is beta. About beta, that is feedback network's gain is If by V naught, and with the feedback, the overall gain is V naught by Is, and current series gain of the amplifier, it is I naught by Vi, and Vf by I naught is for the feedback network's gain, and this is overall gain is I naught by Vs. And for current shunt, it is again, if you noted down the shunt, it is current source. Wherever you got series, you will be having the voltage sources, and if you got the shunt connection, it is the current source. So, it is II, and this is for amplifier gain, this is beta feedback gain, and this is the overall gain. So, that is all about the gain of the amplifier of the feedback network and the overall gain for all the types of feedback connections. And now we are going to see about the gain with the feedback voltage series feedback network. For voltage series feedback network, how the gain is affected, or how the gain is, or it is increased or decreased. We know that if you have a negative feedback, the gain is always reduced. We know that A by 1 plus A beta is the gain with the feedback, where A is the amplifier's gain and beta is the feedback network's gain. So, this equation we are going to derive from this voltage series feedback network. If there is no feedback, that is Vf is equal to 0, for example, the voltage gain of the amplifier is V naught by Vs. If this Vf is 0, what is the voltage to the amplifier? It is again Vs, right? Vi is equal to Vs. So, V naught by, instead of Vs, you are putting Vi. and if the feedback signal Vf is connected in series with the input, then if the feedback is given again, if the feedback is given, if there is no feedback, then Vi is equal to Vs. If there is a feedback, then this Vi is the effective voltage of these input voltage and the feedback voltage, and it is Vs minus Vf, that is the effective voltage. You have to substitute here. So, V naught is equal to A into Vi. We know that what is Vi if the feedback is given. So, it is Vs minus Vf, and after substituting Vf is equal to beta V naught, because Vf is the feedback voltage. So, it can be written as beta V naught. So, here after substituting beta V naught and this term is taken into the left hand side, you will be getting V naught as a common. So, you will have 1 plus beta A into V naught is equal to A Vs. So, here from this equation, if you calculate the feedback gain with the feedback, it is nothing but V naught by Vs, isn't it? V naught by Vs, and it is given as A by 1 plus beta. So, from this equation, you are getting this factor A by 1 plus beta. What did you infer from this equation? This A is the gain of the amplifier, basic amplifier, and this beta is the gain of the feedback network. So, this AF is the gain with feedback, gain of the circuit with feedback. So, if you give feedback, the gain of the amplifier is reduced by a factor called 1 plus beta A. So, always if you give the negative feedback, then the gain of the amplifier will definitely reduced by the factor of 1 plus beta A. That is what you have derived from this circuit. So, in voltage series feedback, you conclude that if you give the feedback, then the gain of the amplifier will definitely reduced by the factor of 1 plus beta A. And for voltage shunt feedback, what will happen for voltage shunt feedback? Again if you from this circuit, you will, if you calculate what is V naught, what is Is, and if the feedback is given, you will be having the effective voltage as Ii. From this, what is Is you have to calculate, and what is If? You know that If is the feedback signal, the output of the feedback network, and it is given as beta V naught. So, if you substitute everything here, you will be getting the gain of the amplifier as A by 1 plus beta A. So, if you give feedback in any kind of the network, the gain of the amplifier is reduced by the factor of 1 plus beta A. So, now the gain is reduced and it will get stabilized. So, you are having a stabilized voltage gain in the feedback circuits. And if you go with the parameter called input impedance, so what is the effect of feedback on this input impedance? We are going to see whether the input impedance is increased or it is going to reduce, or it will vary according to the type of the circuit. We will discuss now. So, in voltage series feedback network, this is the voltage series feedback. Instead of a block, previously you are having a equivalent circuit of an amplifier here. If you see the block diagram, instead of a block in previous circuits, here if you see the circuit here, you will be having a simple block. Instead of a block, you are having an amplifier equivalent circuit here. This is internal input impedance of an amplifier, this is internal input impedance of the amplifier again, and this is the voltage source. So, this is the internal parameters by which the equivalent circuit has been constructed, and it is replaced here in the circuit. So, for this voltage series feedback, if you calculate the input impedance with the feedback, this is the calculation. So, what is input current II? II is given as Vi by Zi, and this Vi is, what is Vi? Vi is the voltage given to the amplifier, right. So, this Vi can be written as the effective voltage of the input and the feedback voltages. So, this is the effective voltage Vs minus Vf divided by Zi. And what is this Vf again? Vf is the feedback signal out of the network, feedback network. So, it is given as beta V naught, and this Vf is replaced by beta V naught. And what is again V naught? The output voltage. This output voltage can be written as here A is equal to V naught by Vi. The gain of the amplifier is given as V naught by Vi. So, V naught can be written as A into Vi. So, here A into Vi by Zi. This Zi goes to the left hand side. So, the final equation will be like this, and here if you take Vs here and this if you simplify this equation, input impedance with the feedback, it is Vs by Ii is given as Zi plus beta A into Zi, and if you take Zi out, it is 1 plus beta A. This is simple substitutions and simplifications. After this, you will be getting Zi into 1 plus beta A, right. So, here Zi is the input impedance without feedback and Zif is the input impedance with the feedback. And what is the resultant? If the feedback is given, what happens to the input impedance of the circuit? Come to the conclusion that it is increasing, the input impedance is increasing for voltage series feedback. Without doing this connection, you can say for this kind of feedback network, the input impedance is increased because here according to the type of the connection, voltage series. So, voltage is you are taking shunt, you are connecting in series with the input signal. So, if you connect series with the input signal, what happens to the input impedance? The input impedance will definitely increase, because if the resistance is connected in series, what is the value of resistant equivalent if you connect R1 and R2 in series? So, the equivalent value of this particular resistors are the addition of the values of the two resistances. So, it will increase, the resistance will increase. Otherwise, in the other connection in shunt, if you connect it in shunt, for example, if those two resistors is instead of connected in series, if it is connected in parallel, R1 parallel with R2, what will happen to the value of the resistors? It will reduce. For example, if those two resistors have 2 as a value, so you know that the formula to calculate the parallel combination of the resistors. So, R1 and R2, if it is connected in parallel, R1 R2 divided by R1 plus R2 is the formula to calculate the parallel combination of the resistors. So, if both the resistors has the value 2, so 2 into 2 divided by 2 plus 2, so 4 divided by 4, that is equal to 1. So, if those two resistor values is 2 or 2, then it is reduced by half of the value if it is connected in parallel. So, from the circuit connection, you can say that the input impedance value is increased. Similarly, for current series feedback also the input impedance value is increased. Okay. So, for the voltage shunt feedback, what will happen before going to this kind of calculations, you can straight away say that it is connected in shunt. Just now we have seen that if it is connected in parallel, then definitely the values of the resistance will get reduced. So, for this voltage shunt feedback, this is the input impedance value. So, Zi divided by 1 plus beta A. So, the effective value of the input impedance is Zi divided by 1 plus beta. Here if you give the feedback, then the impedance is reduced by the factor of 1 plus beta A. It is also true for the current shunt feedback. Next is output impedance with feedback. Always according to the feedback connection, you can say that for series network it will reduce and for shunt network it will increase. For series network, the value of the output impedance is derived as ZOF is the output impedance with feedback, derived as ZO without feedback divided by 1 plus beta A. So, it is reduced by the factor of 1 plus beta A. This will true for current series feedback. And next is current series feedback. For current series feedback, it is Z0 into 1 plus beta A. So, for current series feedback, it is increased. If it is series, then you know that the value of the resistance will increase. So, it is increased with the factor 1 plus beta A for current series feedback. And this is the comparison table about the input impedances and output impedances for all the various types of feedback networks. For voltage series, input impedance is increased and output impedance is reduced. This is what we need for any electronic circuit. Let us summarize what we have seen today. The types of feedback circuits we have seen, and what is the effect of feedback with the gain, and what is the effect of feedback with the input impedance and the output impedance we have seen. So, these are the questions you have to know. List the different types of feedback circuits and which feedback circuit reduces input impedance of an amplifier, which feedback circuit increases the output impedance of an amplifier, which feedback circuit is suitable for better amplification. One more question, the first one, you have to say that what is the concept of the feedback, that is very important. This is the reference. we come to the end of the session. Thank you.